Imagine a future with no stars, no planets, not even time, just a silent, frozen darkness where nothing changes. That future isn't science fiction, it's written into the fabric of our universe, from the slow death of heat to violent cosmic tears. From collapsing dimensions to the flicker of quantum decay, these are the ways the universe might end. And some of them have already begun. Let's dive in, and remember to like and subscribe if you enjoy this stellar story. This is a small channel, and every interaction from you helps immensely. Each theory paints a different picture of the universe's ultimate demise, from slow fading to sudden catastrophe, yet all are grounded in scientific ideas. Each scenario is explained with its mechanism, scientific status, origin, evidential basis, and the profound implications for matter, space, and time. Humanity has long pondered how the universe might ultimately end, and modern science offers several dramatic scenarios. In this feature-length stellar story, we explore the major theories for the fate of the universe. Each theory paints a different picture of the universe's ultimate demise. From slow fading to sudden catastrophe, yet all are grounded in scientific ideas. Below, each scenario is explained with its mechanism, scientific status, origin, evidential basis, and the profound implications for matter, space, and time. One widely accepted endgame is the heat death, also known as the Big Freeze or Big Chill. In this scenario, the universe continues expanding indefinitely, and over countless eons, it asymptotically approaches absolute zero temperature. As galaxies drift ever farther apart and stars exhaust their fuel, the cosmos slides into darkness and near-empty silence. Eventually, all stars burn out, matter decays, black holes evaporate, and nothing remains except a thin haze of particles and energy at maximum entropy. With no temperature differences or usable energy, all processes grind to a halt. Scientific consensus leans strongly toward this fate. Under our current understanding of cosmic acceleration, the Big Freeze is considered the most likely outcome, given an ever-expanding universe dominated by dark energy. Historically, the idea emerged from 19th century thermodynamics, the heat death concept, and was later applied to an expanding universe once the Big Bang theory took hold. Observational evidence supports this scenario. We see the universe expanding and cooling, and dark energy's push suggests eternal expansion rather than a collapse. If dark energy behaves as a constant vacuum energy, the expansion will never reverse, leading inexorably to heat death. In terms of timeline, star formation in galaxies will cease in about 100 trillion years as gas runs out. Long after, stellar remnants like white dwarfs and neutron stars will cool to black, planets will freeze, and even black holes, the last bastions of structure, will evaporate via Hawking radiation over 10 to the 100 years or more. Space itself will continue stretching, and the cosmos approaches a thin void at nearly absolute zero. The implications are poignant. No life or information can persist when entropy is maximized and all energy sources are spent. The universe ends not with a bang, but an eternal whimper, a cold, dilute expanse where time has little meaning because nothing ever changes. If the expansion of the universe not only continues but accelerates without bound, we face the more violent doomsday of the Big Rip. In this scenario, driven by a form of phantom dark energy even more intense than a cosmological constant, the expansion rate grows explosively over time. Eventually, every bound structure in the universe is torn apart by repulsive expansion. Galaxies would be the first to fly apart, then gravitational bonds within galaxies would fail. In the final moments, stars, planets, and even atoms would be ripped to shreds as space itself stretches at an infinite rate. At the very end, the accelerating expansion becomes so extreme that the scale factor of the universe becomes infinite in finite time, effectively a singularity in which the fabric of space-time is rent asunder. The Big Rip's mechanism requires an equation of state for dark energy with ratio W, 1, meaning the dark energy density increases as the universe expands, sometimes called phantom energy. If such phantom energy dominates, it overcomes all forces binding matter. To illustrate the progression, in one hypothetical model, the Big Rip would occur approximately 22 billion years from now. About 60 million years before the end, galaxies would begin to disintegrate as their stars drift apart. 3 months before the final moment, solar systems like ours would be gravitationally unbound, planets flung away from stars. In the last minutes, stars and planets themselves are torn apart, and 10 to the minus 19 seconds before the end, even atoms are destroyed into subatomic particles. At the instant of the Big Rip, distances become infinite, and space-time itself is ripped apart, terminating the universe in a kind of singularity of infinite expansion. The status of this theory is intriguing but uncertain. It's a logical possibility if dark energy has phantom properties, but current observations do not confirm such extreme behavior. The latest measurements show dark energy's equation of state W is very close to 1, consistent with a cosmological constant. If W is not 1 exactly, a Big Rip cannot occur. However, it's hard to measure exactly 1, and slight uncertainties mean we can't yet completely rule out W1. No direct evidence for a future Big Rip exists. Rather, it remains a theoretical possibility if the cosmic acceleration grows stronger over time. The idea was first described in the early 2000s by cosmologists exploring phantom energy, while not the favoured scenario, since a simple cosmological constant fits the data well. The Big Rip is taken seriously enough to study its consequences. The implications of a Big Rip are as spectacular as they are terrifying. All structures, from galaxy clusters down to atoms, have a finite lifespan in this model. Everything gets unbound. Matter is ultimately reduced to elementary particles and unzipped space-time in a final, abrupt calamity. Unlike heat death, which leaves a cold memory of the universe, a Big Rip would erase the universe entirely in a last convulsive burst. For any hypothetical observers, there would be no safe haven. As the end approached, even molecules in one's body would fly apart. Time itself would cease, as distances become infinite. Though highly speculative, the Big Rip presents the universe dying in a kind of anti-Big Bang, an explosive runaway expansion that tears apart reality. In stark contrast to eternal expansion, the Big Crunch is a theory in which the expansion of the universe reverses into a collapse. Here, gravity, or some other attractive force, eventually gains the upper hand. If the average density of matter or energy in the cosmos is high enough, or if dark energy somehow becomes attractive, the expansion will slow, stop, and then reverse into a contraction. Over extremely long timescales, galaxies would start rushing back together. The night sky would brighten as galaxies blue, shift, and crowd closer. Ultimately, all matter and space would collapse toward a final singularity, a state of infinitely high density and temperature, mirroring the Big Bang in reverse. The entire universe would shrink to a point, or something akin to a black hole containing all existence, possibly ending time as we know it. The Big Crunch was a major contender in 20th century cosmology, when it was unclear if the universe's expansion would go on forever. Historically, many scientists expected gravity might slow expansion and cause recollapse if the universe's density was above a certain critical value. This is tied to whether space is closed, finite and curved like a sphere. A closed universe with no dark energy naturally leads to a crunch. Early on, theoretical models allowed this symmetric fate. The universe could cycle from Big Bang to Big Crunch. However, the discovery of accelerating expansion, dark energy, in 1998 upended that expectation. Current evidence suggests a Big Crunch is unlikely under known physics. Measurements indicate the universe is very nearly flat and dominated by repulsive dark energy, not the kind of gravity-only cosmos that would recollapse. Still, a Big Crunch cannot be entirely ruled out. If dark energy were to weaken or turn into gravitational attraction, the universe could stop expanding and fall back on itself. In terms of mechanism, a pure Big Crunch requires that the collective gravity of matter and any attractive dark energy halts the expansion. Galaxies would begin to move toward each other. Eventually, all galaxies merge as space contracts. Background radiation would heat up again as volume shrinks. Stars might ignite anew in collisions. In later stages, even atoms and subatomic particles would be squeezed together in extreme conditions as the universe's scale collapses towards zero. At the final moment, the crunch singularity, known physics, breaks down. Quantum gravity effects would dominate, and it's conceivable that all dimensions of space become a single point of infinite density. From the outside, if one could imagine such a viewpoint, the universe would vanish into a massive black hole-like state. The implications for matter, space, and time are profound. All matter would ultimately fuse and obliterate in the crushing density. Time might end as the flow of cause and effect is destroyed by infinite gravitational curvature. Some cosmologists have speculated that a big crunch could also be a bounce, more on the big bounce next, meaning the end of one universe could seed the birth of another. Absent that, the big crunch is a final end state, a fiery collapse where space contracts to nothing and all distances shrink to zero. For any life forms, a contracting universe would first appear hospitable, galaxies closer together, then lethal as intense heat and radiation increase. While modern data makes this outcome unlikely in our universe, it remains a key part of cosmological theory, a natural counterpart to the Big Bang in the symmetry of Einstein's equations. It's a reminder that under different cosmic conditions, the sky could fall and bring everything back to an eternal night of infinite gravity. Is an ending truly the end, or could it be a new beginning? The Big Bounce hypothesis suggests that our universe may not terminate forever, but rather undergo a cycle of death and rebirth. In a Big Bounce scenario, the universe's end, such as a big crunch, triggers an event analogous to another Big Bang. The cosmos bounces from contraction to a new expansion. In other words, the universe could be oscillatory or cyclic, with each cycle comprising an expansion phase followed by a contraction and subsequent re-expansion. The Big Bounce offers a possible resolution to the question of what happened before the Big Bang. It might simply have been the end of a previous universe. There are multiple theoretical models for how a bounce could occur. In classical general relativity, a true bounce is hard to achieve because a collapsing universe tends to hit a singularity, infinite density. However, quantum physics or new gravity theories could intervene. For example, loop quantum cosmology, an application of quantum gravity, suggests that extremely high densities might create a repulsive force, quantum pressure, that halts the collapse and drives re-expansion, avoiding a singularity. Similarly, string theory-inspired ekpyrotic models propose our 3D universe is a membrane, brain, that periodically collides with another brain, causing big bangs. After each collision, the universe expands, then eventually slows and contracts for the next collision. In these models, entropy and other issues are handled by the physics of extra dimensions, e.g., entropy is diluted during the brain separation. The idea of cycles also appeared in conformal cyclic cosmology, CCC, Sir Roger Penrose's proposal that the remote future of one universe, emptied out by expansion, can be mathematically transformed into the Big Bang of a new one, essentially a bounce in a very abstract sense. Historically, the concept of an oscillating universe dates to the early 20th century. Einstein himself, after formulating general relativity, toyed with the idea of a cyclical cosmos, though he never fully developed it. Richard Tolman, in the 1930s, studied cyclic solutions. The idea fell out of favor when the Big Bang and one-time expansion became well supported by evidence, like the cosmic microwave background. However, cyclic models saw a resurgence in the early 2000s with new theoretical insights, brain cosmology, loop quantum gravity, attempting to address the Big Bang singularity and other puzzles. Observationally, current evidence doesn't show signs of a previous cycle. For instance, we haven't found clear remnants of a pre-Big Bang universe in the cosmic background. Claims of anomalous circles or patterns are unproven. Also, measurements indicate the universe's spatial geometry is flat and will not recollapse on its own. This means a classical big crunch needed for a bounce is unlikely without new physics. Moreover, each cycle would have to somehow avoid accumulating entropy, the entropy problem. Otherwise, successive bounces would get larger and longer, and eventually the universe would end in heat death rather than bouncing. Some advanced models handle this via exotic physics, as noted, e.g. brane expansion, resetting entropy each cycle. But it's speculative. If a big bounce is what awaits us, the implications are almost hopeful in a cosmic sense. The end is not final. Matter, space, and time would be crushed in a contracting phase. But out of that destruction, a new universe would be born, potentially with new galaxies, stars, and maybe new life. It means time might be cyclic or infinite, and our universe could be just one episode in an endless series of universes. On the other hand, from our perspective, within one cycle, a big crunch bounce still means doom. In the approach to a bounce, temperatures would skyrocket and everything we know would be incinerated or merged into an ultra-hot plasma as the universe shrinks. At the bounce point, physics we understand ceases to apply. Space and time, as we know them, would dissolve and reconstitute. If the bounce leads to a new Big Bang, that next universe might have entirely different properties. While the Big Bounce idea remains theoretical and outside the mainstream for now, it provides a grand vision of a cosmic phoenix, an eternal regeneration of universes, rather than a one-and-done finale. Not all hypothetical cosmic finales are as orderly as a gradual freeze or a symmetric crunch. Some theories predict sudden singularities, abrupt, violent endpoints that arise seemingly out of nowhere in the future expansion. In these scenarios, the universe could hit a cosmic wall or tear at a specific moment in time, even though expansion until then might have been moderate. A singularity, here, means some physical quantity becomes infinite, density, pressure, curvature, in finite time, causing physics to break down, unlike the Big Rip, a type of singularity where the scale factor blows up. A sudden singularity might occur without the universe needing to stretch to infinity beforehand. One example is sometimes called a big break or type 2 sudden singularity in classifying cosmological models. In such a model, the universe's scale factor, size, remains finite at the singular time, but higher derivatives, like the deceleration or jerk, diverge. For instance, the expansion might slow down rapidly, and then at a critical moment, the deceleration becomes infinite, essentially bringing expansion to a screeching halt with an infinite jolt. This would be catastrophic. Matter experiences an infinite tidal force or pressure, even though space itself isn't stretched beyond all bounds. Another variant is the so-called Big Freeze singularity, not to be confused with the Big Freeze heat death, classified as type 3, where the scale factor approaches a finite value, but the density or pressure blow up to infinity at the endpoint. In all these cases, the universe ends at a finite time with a nasty singularity, a tear in space-time that appears suddenly. Where do such models come from? Typically from considering exotic equations of state for the cosmic fluid or modifications of gravity. For instance, certain hypothetical dark energy components or scalar fields could evolve in a way that causes a future singular behavior. In the mid-2000s, cosmologists explored these possibilities to classify all kinds of finite time future singularities beyond the standard ones. These studies showed that, mathematically, nothing in general relativity forbids a sudden singularity if the energy conditions are tweaked. It's a solution to the equations, though whether any physical substance could cause it is unclear. In some brain world models or specific dark energy models, you can get a universe that expands normally, then at a critical density or time, a singularity pops in. One could imagine, for example, a phantom-like dark energy that doesn't quite rip everything apart gradually, like Big Rip, but instead leads to a divergent pressure at a moment, pressure singularity. No direct evidence or consensus supports a sudden singularity happening, as it relies on very speculative forms of energy. Observationally, we'd have no warning until the mathematical fate is nearly upon us, by definition, it's sudden. The notion is more of a theoretical exercise. If we allow unusual properties in dark energy, the universe's fate could be a surprise ending. Because it's not tied to a common term like Big Crunch or Big Rip, the sudden singularity idea is not well known outside academic circles. Yet, for a documentary narrative, it provides a startling twist. The universe could end abruptly out of the blue. Imagine living your life in a fairly normal expanding universe, only to have the cosmic expansion hit an infinite barrier at a certain time, beyond which the equations say reality cannot continue. The implications of a sudden singularity are fatal in the extreme. At the singular moment, some physical quantity, perhaps tidal force or cosmic pressure, becomes infinite everywhere. That would likely shred any matter instantaneously or disintegrate atoms by infinite tidal forces. It might also imply time cannot progress beyond that point. Time literally stops because no extension of space-time is possible past the singular event. Unlike heat death, where the universe fades out, or even a big rip, which, though sudden at the end, is preceded by a clear ramp-up in destructive power, a sudden singularity could catch the universe by surprise. One moment, everything might look normal. The next, a cosmological parameter blows up to infinity and the universe is ended in a flash. This unsettling possibility serves as a reminder that esoteric physics could, in theory, spring surprises on the fate of the cosmos. While it's not part of the standard toolkit of likely futures, it's scientifically credible as a solution to general relativity under exotic conditions, making it a chapter of doom we cannot completely ignore. Gap 5-8, a recently proposed twist on the heat-death concept is the long freeze, a quiet cosmic apocalypse that shares features of the big freeze, but with a critical difference. The expansion of the universe comes to a complete halt. This theory emerged from explorations of a holographic dark energy model, a speculative idea tying dark energy to quantum gravity via the holographic principle. In the long freeze scenario, dark energy is not a constant, but rather a phenomenon that gradually dissipates over time, eventually dropping to zero strength. As dark energy fades, the driving force of expansion weakens. The expansion of the universe slows down and finally grinds to a stop at some finite time in the future. The cosmos would then reach a fixed maximum size, effectively frozen in terms of growth. Once expansion ceases, the universe doesn't recollapse. It simply stays static or coasts forever. However, with no new energy being injected and no expansion, entropy still increases. Stars will continue to burn out and no new stars will form because galaxies have used up their gas. In this frozen but slowly decaying universe, the remaining stars die one by one, turning the sky black. Over an extremely long, quiet period, the universe enters a dark era similar to heat death. Black holes are the last enduring structures, but even those eventually evaporate, leaving nothing but weak background radiation. The term long freeze emphasizes that this end involves a long, drawn-out fading of the lights after expansion has stopped. It's like a cosmic twilight that never quite gets to midnight until, perhaps, an eternity passes. The contrast with the classic Big Freeze is that in the standard Big Freeze, heat death, the universe keeps expanding forever, diluting matter and energy to near nothingness. In the long freeze, by contrast, the expansion itself freezes in place, stops, at some final volume. Entropy still wins. Stars twist tea and everything goes cold. But the universe's size is fixed rather than endless. In practical terms, for anyone within the universe, both scenarios end up fairly similar, darkness and death. But theoretically, the distinction is important. In a halted expansion universe, there could be subtle differences in how the very far future plays out. For example, the cosmic microwave background temperature would bottom out at a slightly higher value than absolute zero, since volume isn't infinite. The long freeze concept was described in a 2023 paper by a pair of US and Indian researchers, and it generated interest because it ties into ideas about quantum gravity and holography. What would evidence for a long freeze look like? Essentially, this scenario would require that dark energy is not constant but decays over time towards zero. Some recent astronomical surveys have hinted, though not confirmed, that dark energy might be evolving to be weaker. More on that in the next section. If those hints firm up, one possible outcome would indeed be a coasting or stopping of expansion in the distant future. However, the long freeze specifically comes from a particular theoretical framework, holographic dark energy, and that framework is far from established. As of now, the long freeze is a speculative scenario, an interesting hybrid of ideas rather than a widely endorsed fate. It serves to stress test cosmological theories. If our universe has properties suggested by certain quantum gravity ideas, what end state do they predict? In this case, the result is a finite static universe slowly decaying away. The implications of a long freeze are, in a word, quiet. There is no bang or crunch, no sudden rupture. Instead, cosmic motion itself dies out. Galaxies would no longer recede from one another once expansion stops, but without new energy, the stars within them will age and extinguish. It's a solemn vision, a universe that one day just stops growing, as if time has run out on expansion, and then slowly decays into stillness. For an incredibly long time after expansion halts, things would look almost normal. Galaxies in place, perhaps orbiting within clusters, but generation by generation, the stars go dark, planets freeze, and black holes swallow remnants until Hawking radiation erodes even those. Space remains vast and silent, a graveyard universe of old, cold embers and expanding darkness, though not expanding further in volume. In effect, the long freeze shows that even if cosmic acceleration doesn't rip us apart or last forever, the end result is still a frozen, lifeless eternity. Whether the universe expands forever or stops expanding, if no new physics intervenes, thermodynamics ensures a final darkness. Gap 5s. Up to now, we've assumed dark energy either stays constant, leading to endless expansion, or is phantom-like, leading to a big rip, or fades to zero, coasting to a freeze. But what if dark energy does something even more dramatic? What if it decays or turns attractive? The term dark energy decay refers to a class of scenarios where the mysterious dark energy that's currently accelerating the cosmos changes over time, potentially reversing its effect. If, for instance, dark energy is due to a field that loses strength, the cosmic acceleration could slow down. In an extreme case, dark energy might disappear or even become negative, meaning gravity would again dominate and pull the universe back together. This could lead to a re-collapsing universe, essentially reviving the possibility of a big crunch. The current scientific debate on dark energy touches on whether it's truly a constant or a dynamic entity. The simplest model, and the one that fits data so far, is a constant vacuum energy, cosmological constant. But astronomers have been testing this by looking at the history of cosmic expansion. Recent findings by projects like DESI, Dark Energy Spectroscopic Instrument, have raised eyebrows by suggesting that dark energy's effects at earlier times might differ slightly from today. These results appear to fit better with a dark energy that diminishes over time rather than one that stays constant. If this is true, then in the far future, the accelerating expansion could slow to a coasting expansion and perhaps eventually stop. Some optimistic interpretations even imagine dark energy could switch sign to become attractive, effectively a negative pressure that induces collapse. That would indeed result in the universe ultimately contracting in a big crunch. It's important to note that these are speculative extrapolations. Katie Mack, a cosmologist who studies cosmic endings, has pointed out that even if current data hint at evolving dark energy, we have no guarantee what it will do next. It could weaken, vanish, oscillate, or do something unexpected. Until we identify what dark energy actually is, predicting its far future behavior is guesswork. Nonetheless, the notion of dark energy decay is scientifically plausible. Dark energy might be a field, often called quintessence, that slowly rolls down a potential, thus changing over billions of years, or it could interact with other components, causing its density to drop. If it decays completely, we'd be left with just matter, radiation, etc., and presumably an expansion that slows and asymptotically stops, like the long freeze scenario. If it decays into something with negative pressure, or effectively morphs into a kind of dark matter, it could trigger a contraction. From an observational standpoint, scientists are actively seeking any sign that dark energy's strength varies with time. So far, any variation is at most slight. But the mere possibility motivates thinking about how the universe ends if dark energy isn't a perpetual constant. If dark energy fades away, the long-term fate might revert to a classic big freeze, just a bit less cold than with dark energy since expansion halts. Or if it turns negative, a big crunch could ensue after tens or hundreds of billions of years of slowing expansion. Intriguingly, the DESI Galaxy Survey's early results in 2025 suggest the universe's expansion a few billion years ago might have been a tad slower than expected for a constant dark energy, as if dark energy was weaker then. If true, maybe in the future it continues to weaken. However, Mac urges caution. Even with that data, we can't reliably predict the future without knowing the mechanism. Dark energy could have surprises. For example, it might weaken, then later strengthen again. Some theories allow such oscillations. The implications for the universe if dark energy decays are significant. In a mild case, the acceleration subsides and galaxies no longer rush away exponentially. Distant galaxies might remain visible far longer than in the standard scenario, where eventually they'd recede beyond our horizon. A coasting universe might allow structures to remain gravitationally connected on larger scales, but even with no dark energy, an expanding universe, unless it fully reverses, still faces heat death eventually. Stars die, etc., just perhaps at a different pace. On the other hand, if dark energy becomes negative, the relatively peaceful sky would eventually start to collapse. Countless years of slowing expansion would give way to contraction. Galaxies would move towards each other. Eventually, the night sky could grow brighter and hotter as background radiation blue shifts. The universe might recollapse into a fiery crunch, destroying, or maybe rebooting, everything. For now, dark energy decay is an unfolding story. It reminds us that our fate is tied to the fate of this mysterious component that makes up 70% of the cosmic energy balance. Whether it dwindles or dominates will decide if we freeze alone in the dark, or perhaps get a second chance via a cosmic rebirth, or simply a final crunch. Among the most chilling end-of-universe theories is vacuum decay, often nicknamed the Big Slurp. This scenario isn't about cosmic expansion at all, it's about the stability of the very fabric of reality. It hinges on the idea that what we call empty space, the vacuum, might not be truly stable. Instead, we could be living in a metastable vacuum, a kind of temporary, high-energy version of nothingness that could, in principle, fall to a lower energy state. If that happens, it's game over for our universe. The mechanism comes from quantum field physics, particularly the Higgs field that permeates the universe. The Higgs field's potential can be imagined like a landscape of hills and valleys. Our current vacuum is like the Higgs field sitting in a valley, but it might not be the lowest valley, ground state. It could be perched in a secondary valley, a false vacuum, that is separated by an energy barrier from the true lowest valley. If a random quantum fluctuation or a high-energy event gives the Higgs field, or any similar field underpinning physics, a hard enough push, it could tunnel through the barrier and roll down to the deeper valley, the true vacuum. This is called false vacuum decay. It would produce a bubble of true vacuum that would nucleate at the point of the fluctuation. What happens next is terrifying. The bubble of true vacuum would expand at near the speed of light in all directions. We wouldn't see it coming. It would arrive roughly at light speed, so no warning. Everything the bubble touches would be fundamentally altered. Inside that bubble, the laws of physics might be different because constants of nature, like particle masses, force strengths, are determined by the vacuum state. The bubble could have a lower energy density, but critically, if the difference is big, it releases an immense amount of energy as it expands, essentially an apocalyptic shockwave sweeping the universe. The walls of the bubble carry tremendous energy and would incinerate anything in their path. At the bubble's forefront, particle bonds would break, atoms would likely disintegrate. Moreover, if the true vacuum's physics doesn't support the structures of matter we know, then atoms, nuclei, maybe even protons could decay or dissolve in its wake. In essence, it's the destruction of the universe as we know it, being replaced by something utterly alien inside the bubble. To make matters worse, the bubble expansion is self-perpetuating. Once a true vacuum bubble forms, it's energetically favorable for it to keep growing, converting false vacuum to true vacuum. There's no stopping it. It would consume the entire observable universe and far beyond. This is why it's described as the ultimate cosmic catastrophe. Not only is life impossible in the new vacuum, chemistry, as we know it, is impossible. It's not even clear if particles, as we know them, would exist. Some calculations by Sidney Coleman and Frank de Luchy in 1980 suggested an extra twist. If the vacuum energy in the true state is sufficiently lower or negative, the bubble might not just expand, it might trigger a gravitational collapse as well. In that case, the bubble interior could collapse into a singularity almost instantly. Either way, for observers, it's effectively instant annihilation. One moment you have a functioning vacuum around you, next moment you're either inside a bubble where physics has been rebooted and you're gone, or everything ends in a crunch inside the bubble. Is this just science fiction? Amazingly, vacuum decay is taken quite seriously by physicists because it arises from known principles of quantum mechanics and our measurements of the Higgs boson. In fact, given the measured mass of the Higgs, around 125 GeV, and the top quark, our standard model of particle physics implies that our vacuum is likely metastable. Barely so, but not in the lowest possible state. The estimated lifetime for vacuum decay, if these were the final story, is immensely long, on the order of 10^139 years by some rough calculations. That's a 1 with 139 zeros years. So the good news is it's incredibly unlikely to happen anytime soon. In fact, there are reasons to suspect new physics, new particles or forces beyond the standard model intervene and make our vacuum truly stable. The early universe's survival through high energy inflation is one hint that either vacuum decay doesn't happen or the parameters were just right to avoid it. So while it's possible, most physicists aren't losing sleep over vacuum decay. As one reassuring point, even if a high-energy collider, like the Large Hadron Collider, could in principle trigger vacuum decay, which was a theoretical concern at one time, the universe has already experienced far higher energies naturally, e.g. cosmic rays, early universe, without vacuum decay occurring. So it's either extremely rare or new physics forbids it. Nonetheless, vacuum decay stands out because it's a fundamental, quantum-driven doomsday. It's like the floor dropping out from under reality. The implications are absolute. Everything, matter, galaxies, physical law, would be rewritten in an instant. If the new vacuum has lower energy, the universe could end up in a state where nothing organized exists. If the vacuum has negative energy, the entire region might recollapse into a hot bubble Big Bang or a singularity. There is even a multiverse interpretation. Perhaps our universe, our bubble of false vacuum, could tunnel and become a tiny part of a larger multiverse, in the sense that the true vacuum bubble that kills our universe is actually a new universe expanding. But from our vantage point, that's no consolation. As one physicist put it, vacuum decay is the ultimate ecological catastrophe. After it, not only is life impossible, so is any structure that could potentially lead to life. It is the swiftest and most thorough end to the universe one can imagine, an instantaneous quantum collapse of the cosmos that could happen at any time without warning. Fortunately, based on what we know, the odds are extremely low and the time frame immensely long. But in the grand timeline of a dying universe, it remains a lurking possibility. Gap 5, yes, beyond vacuum decay, there's a broader notion that the end of the universe could come from quantum processes in unexpected ways. Call it a quantum collapse or quantum transition of the cosmos. In essence, quantum physics, with its inherent unpredictability, opens the door to rare events or shifts that could abruptly change the fate of the entire universe. Vacuum decay is one prime example. A quantum tunneling event destroys the universe, but here we consider the idea in a more general sense as well. One could imagine, for instance, a scenario where fundamental constants or forces suddenly change due to some quantum effect. If, say, the strength of electromagnetism or the masses of particles shifted even slightly, atoms could no longer hold together and matter would dissolve. In a way, vacuum decay is exactly that, a shift in the underlying field that changes constants, and the world as we know it would collapse like a house of cards. But even apart from the false vacuum scenario, physicists have pondered whether other quantum phenomena might trigger cosmic destruction. For example, there are hypotheses, very speculative, about quantum gravity instabilities. Perhaps a tiny black hole could quantum tunnel into existence and rapidly grow, or spacetime itself could undergo a quantum phase change. While these are not supported by evidence, quantum theory often surprises us, and, when extrapolated to cosmic scales, it can produce wild possibilities. Another angle is the quantum fate of a de Sitter universe. De Sitter space is a model of an eternally inflating, exponentially expanding universe like ours with a cosmological constant. In such a space, there is a horizon and a kind of temperature associated with it, similar to black hole horizons. Over an absurdly long timescale, quantum fluctuations might cause rare events. For instance, there's the concept of a Boltzmann brain, a random fluctuation assembling a self-aware entity out of the void in trillions upon trillions of years, more relevant to an end scenario. Given infinite time, a tiny chance event could occur where a new Big Bang bubbles off or the universe's large-scale state fluctuates. In a heat-dead universe, quantum mechanics allows, with vanishingly small probability, a reversal of entropy locally. So, one might say, given enough time, the universe could randomly reset itself by birthing a new ordered patch, essentially a new universe popping out of the old. This isn't so much an end as a bizarre kind of regeneration, but from the perspective of the original universe, it's a drastic transition. The original order is gone and something new begins, which could be seen as the end of the old universe's story. When we speak of quantum collapse, we also evoke interpretations of quantum mechanics at a universal scale. In the many worlds interpretation, for example, the wave function of the universe never collapses. It just keeps branching. But in a hypothetical alternative where some dynamical collapse law exists, Penrose and others have speculated gravity might cause wave functions to collapse. One might wonder, could the universe's wave function collapse? If an observer beyond the universe caused a collapse, would the universe cease to exist or radically change its state? This drifts into philosophical territory. By definition, nothing outside the universe should be observing it, and standard quantum mechanics doesn't include an external collapse for the whole universe. Still, it's a thought-provoking notion of an end. The universe as a quantum system could spontaneously drop into a different eigenstate. If that state is something like a void or a singular state, that's an end. However, these ideas are extremely speculative and not part of mainstream science. In practical terms, whenever physicists talk about quantum-driven ends, vacuum decay is the centerpiece, because it's grounded in well-understood theory. It's essentially the quantum collapse of our metastable vacuum. We've covered how lethal and instantaneous that would be. To reiterate, it's a quantum tunneling event, no bigger than an atomic nucleus to start, that expands to engulf the universe at light speed. It's the ultimate quantum surprise. The lesson here is that unlike the gradual cosmic fades or massive classical crunches, the quantum realm gives us scenarios where the universe's fate could be sealed in a single, tiny, random event. Probability may spare us for unfathomable times, but it doesn't make it impossible. The implications of a quantum-induced end are usually absolute. There's no partial damage. Either it doesn't happen, or it's total. If the universe did end by a quantum transition, it likely means everywhere, everything at once is destroyed or fundamentally altered, because quantum events spread at light speed or faster if they involve a global wave function. This is different from, say, a big crunch where collapse happens over time, or heat death, which is asymptotic. A quantum collapse is like the universe hitting a trigger and instantly shuttering the lights of reality. it's hard to say anything about space and time after that. They might not exist in a meaningful way, or might be reborn in a new form. Thankfully, our best understanding implies such quantum catastrophes are either extremely unlikely or extremely far off. We monitor particle physics results, like measurements of the Higgs field parameters, for hints about vacuum stability. So far, it seems we're metastable, but long-lived. And if new physics makes the vacuum stable, then that particular quantum doom is off the table. Yet, as a chapter in our compendium of ends, quantum collapse reminds us that the universe began with quantum phenomena, the Big Bang itself, and it might likewise end with a quantum twist. The same randomness and uncertainty that allow particles to pop in and out of existence could one day nullify all existence, a ghostly hand casting down the cosmic curtain in an instant. Lastly, we consider a grander perspective. What if our universe's end is tied to something beyond, a multiverse? In the Multiverse Transition scenario, the fate of our cosmos may be to merge, collide, or be subsumed into another universe. If the multiverse idea, born from cosmic inflation theory and string theory, is true, then our Big Bang might have been just one bubble forming in a frothing sea of space-time bubbles. Our universe could eventually encounter another bubble universe, or undergo a transition that connects us to a larger reality. One possibility is a bubble collision. If another universe exists as a bubble expanding in the multiverse, it could, in principle, smack into our universe. The result of such a collision would be cataclysmic for us. It could release unimaginable energy, distort the fabric of our universe, and essentially mix the contents of the two universes, likely destroying structures in the process. Simulations of bubble collisions suggest they would leave detectable imprints, like round scars in the cosmic microwave background. Physicists have actually searched for circular cold or hotspots in the sky that might be relics of an ancient collision, though none have been confirmed so far. If a collision were to occur in the future, from our perspective, it might resemble Vacuum Decay's bubble scenario. Another universe's bubble wall would sweep through at high speed. But unlike Vacuum Decay, which is an inside job where our vacuum just changes, this is an external bubble coming from elsewhere in the multiverse. It would still mean the end of our universe's independent existence. The two bubble universes might coalesce into a bigger bubble, or one might puncture the other. Either way, everything in our universe would be fundamentally altered or destroyed in the collision process. Another multiverse-related ending involves the idea that our universe might simply tunnel or transition into a different part of the multiverse. This is closely related to vacuum decay because in many multiverse models, like eternal inflation, different vacuum states correspond to different universes. If our vacuum finds a route via quantum tunneling to a lower energy vacuum, you could say our universe has transitioned into another universe. In that sense, vacuum decay is not just an end, but also a transit. The universe fades here, but a new region of space with new properties, the true vacuum bubble, is born. So one could frame vacuum decay as the moment our bubble universe joins the rest of the multiverse by becoming a different bubble. It's like our universe opening a door to a new realm, but unfortunately that door slams shut on us as inhabitants. There is also the idea in brain cosmology that our universe, a 3D brain, might eventually collide with another brain in a higher dimensional space. The ekpyrotic cyclic model uses this to cause repeated big bangs. If at some point in the future our brain were to collide with another, that collision would be the end of our universe's current form. It would trigger extreme heating and particle creation, essentially a new big bang that wipes out the old structures. In a cyclic model, this is just one of many cycles, but from within a given cycle, it's an apocalyptic transition. What evidence or status does this have? The multiverse is a highly speculative idea. It's motivated by theories like eternal inflation, which says once inflation starts, it produces an infinite patchwork of bubble universes. Our observable universe would be one such bubble. The idea is polarizing because it's hard to test directly. However, scientists have brainstormed ways, looking for those cosmic background patterns, or maybe gravitational wave signatures of bubble interactions. So far, no convincing evidence of other universes has been found, but eternal inflation is a leading theory for the early universe, and if it's correct, then bubble universes should exist. It's not impossible one could strike us, or that our bubble might one day simply end its inflationary story by merging with something else. The implications of a multiverse transition are mind-expanding. Instead of thinking of the universe as an isolated everything, it becomes a small part of a larger tapestry. Our universe's end would not be the end of all existence. Rather, it's like a cell dividing or a bubble popping in a bigger space-time foam. For us, of course, it is still doom. A collision with another universe bubble would release energy far beyond any supernova or galaxy explosion. It could bathe our universe in lethal radiation and literally reshape space. It might even alter fundamental symmetries, effectively erasing and rewriting reality in the overlap region. If our universe transitions to a new vacuum, everything we know dissolves, and the new vacuum might host entirely different physics. Perhaps a new universe is born, but we are no longer in it. One can think of it poetically. Maybe our universe eventually graduates to join a cosmic, multiversal community, but in doing so, it must shed everything particular about itself. In a multiverse context, space and time, as we know them, might be just local variables. When our bubble ends, say, whether by collision or bubble nucleation, space-time in our bubble ceases to exist in its current form. But the greater multiverse goes on. It's a grander continuity. Our story ends, a larger story continues. Some speculative theories even suggest that black holes might spawn baby universes. So perhaps over cosmic time, our universe might seed new universes as well. Not an end, but a branching. However, those offspring universes will be separate. For us, the result is still that our universe's contents are lost to that larger structure. In summary, the Multiverse Transition chapter is about looking beyond our cosmos and realizing the end might come from outside. It frames our fate as possibly being decided by events in a higher realm of reality. While highly theoretical, it ties together with vacuum decay and big bounce concepts, giving a perhaps bittersweet consolation. Even if our universe ends, the multiverse might recycle its ingredients into something new. As Jodie Foster's character in Contact said, "I'm not sure if it's heartbreakingly lonely or reassuring, the idea that our universe might be one of many. In the context of the end, it's both terrifying, we could be erased by another universe, and awe-inspiring, we're part of a much larger cosmic ecology." For a documentary, it's a fitting final chapter to leave viewers pondering, not just the end of everything we know, but the possibility that everything is far more than we know. In closing, all these theories, from the slow freeze to ripping, crunching, decaying, and beyond, highlight the incredible extremes our universe might undergo. The current best guess remains the heat-death big freeze, given what we observe today, but science keeps pushing the boundaries. And new data, like hints of changing dark energy, could tip the scales toward a different fate. Each scenario carries profound messages: the indifferent march of entropy, the violent potential of dark energy, the fragility of nothingness under quantum rules, and the tantalizing chance of rebirth or other universes. For now, these are distant hypotheticals. Trillions of years or more lie between us and any such finales. Yet thinking about the ultimate end enriches our understanding of physics today. It forces us to ask, what is dark energy? Is our vacuum truly stable? Is time infinite or cyclic, or destined to terminate? Every theory of the end is also a theory of great physics, questions of the present. As we gaze up at the night sky, we can appreciate that we live in the springtime of the cosmos. Stars shine now, galaxies thrive, and life has a chance in this era. In the far, far future, the universe will be far less hospitable, no matter which ending prevails. Contemplating these cosmic finales is both humbling and inspiring. In the grand cosmic timeline, our lives and even our species are fleeting flickers. But by using science and imagination, we can foresee the ultimate destiny of the stars and galaxies. Whether the universe freezes in darkness, rips apart, collapses into a fireball, bubbles into a new reality, or simply stops, each outcome is a chapter in the story of the cosmos. We are the universe's way of trying to understand itself, including how it might cease to be. And in that endeavor, every theory of the end is a reminder of how precious the present is, and how extraordinary the universe's journey will continue to be, perhaps even beyond an end into something we have yet to dream. This has been the story of the end to whatever lies beyond the end. If this journey moved you, if it sparked wonder or gave you chills, like this video, subscribe to Stellar Stories and join us again for more voyages into alien worlds, cosmic mysteries, and the breathtaking beauty of science.